Okay, today's lesson we're going to continue with electromagnetic induction, but we're going to look at it slightly different. So let's just quickly review. So remember, if we have a wire that we're going to move inside of a magnetic field, then that's going to induce a current inside the wire. So remember, with our left hand rule, we put our B finger out of the page, we put our thumb to the right. Remember, we want to think of this as moving that electron to the right. So our thumb goes to the right, our B goes out of the page. So then we would get, our force would be upwards in this case. So that means our current, the electrons in that thing, are going to flow upwards. So that's what we did with electromagnetic induction. Another scientist, Lenz, kind of thought of maybe there's a better way to do this type of experiment. Instead of moving the wire through the magnetic field, so that's meant we had to spin it if it was like a motor type generator thing, or we'd have to physically push the wire, but we're not going to be able to do this every time. So he thought, could we be able to do the same thing, but instead of moving the wire, what would happen if we moved the magnet? If you remember from Faraday's law, he said all we need to do is have a changing magnetic field. So that also means that if the magnet moves, we should be able to induce a current as well. So Lenz came up with Lenz's law, and what he did was he was able to figure out which way the current would go in a coil of wire if we move a magnet in and out of it. So imagine a coil, kind of like a toilet paper tube wrapped around with wires, and if we push a magnet through the coil of wire, we should be able to create a current in that coil of wire. So what Lenz figured out was, we're going to push the magnet in or out, either the coil, the wire is going to go, the direction of the current is going to go one way or the other. So the trick was how to figure out which way the current is going to go. So the common sense way, or what most people would think, is what we consider is the wrong way. It's the wrong way of doing things. So if we were to push the north pole into the coil, like the way it is in this diagram, right? We have the north end of the magnet, it's going to push in, where let's just assume that the coil current is going to go upwards like that. So if our coil is going upwards, the current's going upwards, we can use our second hand rule. So our hand would go around upwards, so then our thumb would point to the right. So that means that would be our north pole, that would be our south pole. So if that's the case, that's the way it would work. And what's the problem? Well, if this is going to work this way, we're actually going to not have to do anything. All we have to do is let go of the magnet, and it's going to get attracted to the coil, the north-south coil, and it would create electricity. So if the poles are arranged like that, that means we could get electricity by doing nothing. But we know that from work and conservation of energy, we can't create energy out of nothing. We have to do some sort of work to be able to make that happen. So that means then we actually have the directions wrong. So the right way to interpret Lenz's law is we have to think that the only way we're going to be able to force that magnet in and do work is if this is the north end of the magnet, we have to have the north end of the pole going against it. So those are naturally going to repel. So for us to do work and expel energy, we're going to have to force those things against each other. So if we force the north end against the north, that's going to create work, which then means that work then would get converted to energy. So we still use our second hand rule. Once we figure out that the north end has to be the left side, then our fingers would curl around it, point our thumb to the left, our fingers would coil around it, and we'd see that our current then is going down the wire. So the key to remember with Lenz's law then is we just have to remember that we have to do work. We have to be able to kind of do what's opposite. We've got to force that magnet in the direction it doesn't want to go to create the electricity. So let's go through this example. So we've got in this case, we're going to pull the magnet out of the coil. So you can see our north is getting pulled away. So in this case, if we pull the magnet away, that's going to, for us to do work, we would have to make that the south end of the coil, and that would be the north end. So if we're going to pull the north and south, they're naturally attracted, so we're going to force them apart. So in this case now, if we put our hand, point our thumb to the north, you'd see that our current, our fingers wrap around it, so our current would go upwards around the coil. Okay, so it doesn't matter how the magnet's oriented. It can be north or south either way. The coil can be north or south either way. You just have to make sure that you figure it out so that they repel, or they do opposite to what they want. So if we're going to force it in, we want the north and north to match, or the south and south to match. Okay, so I'll just re-sketch one. It doesn't really matter which way the magnet is. So if we were going to force this into the coil, if we're going to go inwards, we want the souths to be against each other. So then we'd point our thumb to the north end of the coil, and we'd figure out our direction of the current that way. If we were going to pull it away, that same magnet, north and south backwards, then this would be the north end because we're going to break that attraction, and our direction would be opposite. Okay, so the key thing is figure out what the direction of the north and souths are to either attract or repel, and then from there you can use your hand rules to figure out the direction of the current. And that's all.